Hello, this is Jim Corkins, and we are moving on to we're continuing with our 1.0.2, and this is going to be in position versus time graphs. So we're going to be starting graphing and how to graph motion in one dimension using position versus time graphs. If you haven't done the reading, please do so. CLETA chapters 1, 2, and 3, or if you're doing OpenStax in college physics, chapters 2 and 3, or if you're in 121, chapters 2, 3, and 4. Also, please get started on the sapling homework if you haven't already done so. All right, here we go. So let's go ahead and let's try to do some. Let's start off wherever your experiences are. What I want you to do is take a moment and interpret what this graph means. Okay. And obviously, this is a position versus time graph, so you're going to have to pay attention to the vertical and horizontal axes and what they're labeled as, but also take a look at the units of those and also the scale. The data point is the data points are is the red line. So go ahead and interpret this graph. As well as not only just the data, but also the meaning of the graph, and to try to describe what is happening. Okay, and if you have any experience using linear equations, and what I mean by linear equations, let me go ahead and mark up the document here. We're going to hit comments, and I'm going to close that out. And I mean linear equations as far as y is equal to mx plus b. Okay, so so this is a linear equation. So try to apply this general linear equation that you learned in algebra to this position versus time graph. So go ahead and pause the video and describe what is happening, and try to create a linear equation that predicts the data. So I very overtly left information out so that it would leave you, the responsibility to interpret the graph, leave you with the responsibility of how to interpret the graph. Okay, so let's describe the, forget about the red line for now. Let's just describe what this graph is saying, what the axes are saying. So the vertical axis is position in meters, okay? The horizontal axis is going to be time in seconds, okay? So the first thing I do is look at what the labels are. The next thing I'm going to do is take a look at the increments of that. So this is going to be the 5 meter mark, so that must mean this is the 4 meter mark. This is the 3 meter mark, 2 meter mark, 1 meter mark. Right? So these are all in meters. Erase that for a second. Okay. So those are the meters, right? And these are positive positions, I should say, too. So this is actually positions, and it's not a distance, it's a position. That means this actually could have a negative down here. There could be a -1 position from what we learned last time, -2, -3, and so on, right? So there could be negative positions. So this would be an axis, and we're going to actually relate that to a horizontal axis. So, oops, I'm going to try to, I'm going to take a shape. I haven't done this in a while. I'm going to take a line. I'm going to draw a horizontal axis so I could describe my motion. And then I'm going to actually create a number line for this so I could describe what is happening at the same time that I'm talking to. So this is going to be the 0 meter mark. This is the 1 meter mark. This is the 2 meter mark. This positive 2 meter position. This is positive 3 meter position, positive 4 meter position, and positive 5 meter position. And this is the direction of positive x. So we're going to describe this as a horizontal motion. Just like before, this is going to be -1 meters, -2 meters. I'm trying to make sure these are equally spaced. -3 meters, -4 meters, and then -5 meters. And so this will be the negative x direction, continuing on. Okay? So I drew an axis to kind of help me interpret what is going on here. So these are positions, and if you look at it for the time intervals, this is going to be 0 meters right here. So this is 0 meters. That actually is also 0 seconds on the horizontal axis. And this is going to be 0.25 seconds. This is going to be 0.5 seconds. And 0.75 seconds. And then 1 second. And how I got that is if this is 1 second and it's broken up into quarters, then these have to be quarter-second marks, right? So you have to kind of, well, use hypothetical deductive reasoning, and then you have to induce the rule. So that's kind of what I was doing there. So right here at this point right there, this is going to be the 0 meter mark. And this looks like where the object is starting out at 0 seconds. So this is the start. Okay, so the start is at the 0 meter mark, and that occurs, this object at time 0, the object is at the 0 meter mark, right? Okay, at time 0.25 seconds, it looks like it might be at pretty close the 1 meter mark. Right? Maybe a little bit over that. I'm not sure. So I'm going to say this is at the 0.25 second mark. It's right here, just a little bit over that. At the half second mark, it looks like it's at 0.5 seconds. Maybe I should use a different color. Maybe I should be using red. I'm going to change this. So this is 0 seconds. 0 seconds. This occurs at 0.25 seconds. It's at the 2.5 meter mark at 0.5 seconds, right? So right here is the half second mark, and it looks like it's at 0.25. 2.5 meter mark at that point, at the 0.5 second mark. At the 0.75 second mark, it looks like it's almost to 4. So 0.75 second mark. And then finally, at the 1 second mark, it looks like it's at 5. Okay. So you have an object starting out at a position of 0. So its initial position is 0. 0 seconds. Its final position is at 1 second. Is at, oh boy, I'm saying position and time. Sorry about that. So it's at the final time. This is the final time. The initial time is 0 seconds, right? So at 0 seconds, it looks like it's at the 0 meter mark. So the initial time is 0 seconds. And it looks like at the final time, that's at the 1 second mark. And that would, it'll be at the 0, it'll be at a position of positive 5 meters, right? So its total displacement now is going to be, and I should use a black pen again. Total displacement is going to be x final minus x initial. and that'll be 0 meters minus, so it'll be 0.5, a position of 0.5 meters minus a position of 0 meters. So that will be positive 5 meters. It moved in the right direction, in the positive x direction, a total distance of 5 meters. So it had a displacement of positive 5 meters. Okay. Well, let's change this equation right here. This is the y-intercept, right? Well, the y here is referring to the y-axis. In this case, we're trying to predict the final position of the object. So this y is actually the final is the last data point occurring, and that occurs at the positive 5 meters mark. Well, in this general equation, you're trying to predict the final data point on the y-axis using the x-axis. All right. Well, where did the object start out at in this? Well, it started out at the 0 meter mark, right? Well, that is the y-intercept in this case. So in a motion, a position versus time graph, when you're using a general equation, this y-intercept is most likely going to be your initial position. Okay. What's the name of the x-axis now? Well, that's time. So that's going to be a change in time, and that is going to be our x-axis. And the slope here, let's take a data point right here and choose this. And choose this as the slope. Okay. Well, slope is going to be rise over run, right? Well, if you've heard, the slope can be positive or negative, right? So it could be positive or negative, and rise over run is meters per second, right? Well, meters per second is kind of like miles per hour, right? Well, what is miles per hour? Well, a mile per hour is speed, right? So a meter per second is speed. But since this has a slope attached to it, and it could be a positive slope like we have here, or a negative slope, that also has direction associated with it too. So this is going to be the velocity. Okay? So we're going to transform this equation right here in and use the context of position versus time, and it becomes trying to predict the final position, and that's equal to the velocity over the entire case. It's a constant velocity, delta t plus the initial position. In other words, it's equal to the final position, the final y data point. That's equal to the slope times the x-axis plus the y-intercept, which is the initial position in this case. Okay. Up here on the graph, well, what is this slope in this case, right? Do you guys remember how to get slope? So slope in this case is going to be the velocity, which is going to be rise over run, which is actually displacement over time. Displacement over the total time. Well, we said over here, our displacement is 5 meters, or positive 5 meters, right? And what's the total time? 1 second. Well, in this case, this object is going to have a velocity, and that's a positive slope, so it's going to have a positive velocity of 5 meters per second over the total time, plus the initial position, which is starts out at a y-intercept, or the initial position of 0. Initial position occurs at the initial time. Okay? And so that's really the long-winded interpretation of a position versus time graph. Okay. So this object started out, and I'm going to use a different color. Let's use green. So it started out at the 0 mark. It moved, and maybe I should lay down a vector, an arrow. It moved to the right, Oops. I'm going to draw a vector. Oh, come on. Come on, computer. I guess you can't lay it. I'll have to draw it. I'll have to do it the hard way. Well, I'm going to draw it. So it started out here at the 0 second mark. It moved all the way to the 5 meter mark. So it started out at 0 seconds and moved to the 1 second over a period, over a distance of 5 meters. And so its velocity is, so notice that vector is to the right, and its length is 5 meters in 1 second, right? So its length is, the length starts here, and this is a vector of 5 meters, and its length is 5 meters, and over the period of time in 1 second, okay? And that kind of goes with what we're seeing here. It's got a velocity, it moved a distance of it moved a positive displacement of 5 meters, so it had a positive 5 meters displacement over the period of 1 second. So a lot of instructors say the interpretation of motion should be 5 meters per second. I like to say it had a displacement of positive 5 meters over the period of 1 second. Okay? And that's probably the most accurate description of velocity. I wanted to include this as basically a summary of what I stated. Okay? So here's a similar graph. In this case, the interpretation is going to be it had this, again, the vertical axis is going to be position, and since that is noted with an X, that tells us that this object is moving horizontally left and right. And this is going to be in kilometers, okay? And the horizontal axis is going to be in time, and it's in hours. You got 1 hour, 2 hour, 3 hour, and 4 hour. And in the vertical axis, its positions are going to be positive 50 kilometers to the right, positive 100 kilometers to the right, positive 150 kilometers to the right, and 200 kilometers to the right. And I didn't put that final data point on this, so I'm going to put here, this is going to be 4 hours. And this will be at a position of 200 kilometers. And these should have little positives, because that's in the positive x direction, which is to the right. Okay? So if you think about it, the velocity vectors, from this, in the first hour, from the 0 to 1 hour mark, it moved a distance of positive 50 kilometers over the period of that 1 hour. Okay, and so that's its slope, right? Since this is a straight line, that first data point, that's the slope there at that first data point. Well, that second data point, it moved another 50 kilometers from 50 kilometer meter position to the 100 kilometer meter position. So this is going to be moving again at another positive 50 kilometers over the period of another hour, right? So that slope occurs right here, okay? And then you have the 3 hour mark, and then finally the 4 hour mark, where this continues on in a straight line. So if the initial velocity here is equal to the final velocity, what you can say is that this is a straight line. Obviously, it's a straight line, but if those slopes are all the same along that line, then that has to be a straight line, and that is what is called constant velocity. When your final velocity is equal to your initial velocity, okay, basically all the instantaneous velocities are the same along this line, then it's a straight line, and that is called a constant velocity. that velocity is not changing with time. Okay? So here is essentially the tactics for interpreting a position versus time graph. Steeper slopes correspond to faster speeds, and what they're talking about here is if you have a graph where you have a very steep slope like this, and again, this is position in the x direction over time, and then you have the same graph, but the slope is this much, right? So they're saying that this steep slope here, that's steep, that is equal to fast. And that's whether or not it's negative too, right? Because you could have a negative slope that is very steep, and that's a steep slope. And then this slope here, not as steep. Oops, I should make that a little bit more interpretable. So this is steep, and this is level, slow, and this is a positive, very positive velocity, and this is just a positive velocity. This is a very negative slope, so but it's still steep, so it's fast. And this is a not so negative slope. So this is only not so negative. So this is a level slope as well, so it's slow. So you could be traveling to the right very quickly or traveling to the right slowly. A negative slope is going to talk about where his positions are decreasing over time. So that's going to be a fast car that's traveling to the left, and this is a slow car traveling to the left. This is a fast car traveling to the right. This level is going to be a slow car traveling to the right. And so that's what they're talking about with number one. That's how you look at the slopes and interpret the slopes. And they're saying that negative slopes correspond to negative velocities, meaning it's to the left. A left or in the y direction, so this is left and right is going to be the x direction. Up and down is going to be in the y direction. Okay. We're not going to be dealing with z directions, so this is y direction. And just know that the slope is a ratio of displacement over time, right? So slope is displacement over time. And it's not just x over t, it's your displacement. It's your final position minus your beginning position. Over time. So it's your displacement over total time. And that is your slope, right? So there is this distinction between slope, as you've been presented in your algebra class, which is just rise over run. Well, when you're talking about the context of position versus time graphs, you have to think of displacement as your slope, displacement over time. Okay? Let's try another one. And this time I want you to do everything. I want you to describe what is happening. We're going to also, and I'm going to put down a number line here for you. Let me pause this for a second. Sorry about that pause. I wanted to put a number line on here that's already pre-created. And that way we could go ahead and use it. Okay, and I try to have 1, 2, 3, 4 markings to the left and 4 markings to the right. That way we could have a look at positive and negative positions. All we'll have to do is fill this in. So this will be useful to help us interpret what is happening. Okay? All right. Well, what I want you to do is go ahead and interpret this graph and describe it, fill in this number line here and describe this motion as it's going left and right. And then also create an equation, and I want you to use the actual numbers. You know, you're going to use, I want you to figure out what the velocity is, it's displacement over time, and also the initial and also the initial the y-intercept too. So go ahead and pause the video and fill everything out. Okay, well, I'm going to start this out and I'm going to mark up the document. So I hit the comments and then I hit the arrow to give me more space to write, and I'm going to click on the pencil. Okay, so here we go. I'm going to say that this object looks like it's, well, this is a position versus time graph, and the position again is in meters, so I'm always noting the units. The time is in seconds. Okay, so it looks like this is going to be 4 seconds, so this is going to be 1 second, 2 seconds, 3 seconds. I'm actually going to put the units here, and this is going to occur at the 0 seconds mark, which is right here. Well, that's going to be 0 meters. This is going to be positive 4 meter position, positive 8 meter position, positive 12 meter position, and then positive 16 meters. So it looks like the object starts out at the 16 meter mark, which the positive 16 meter mark, I should say. And that's going to be in our positive x-axis, which is to the right. Here's the 0 meter mark, so it looks like it's going to be 1, 2, 3, 4 units, and units are in 4 meters, so this will be the 16 meter mark. So that starts out, and what I mean by start, at the 0 second mark. It starts out right here. And I'm going to use a different color for that. And then it's at the 12 meter mark. And then it looks like it's at the 8 meter mark somewhere over here. I'm not sure what that is, but I'll put 8 meters here. And then it looks like it ends at the 4 meter mark, right? It looks like it's at the 4 second mark. And I'm just going to call that 4 seconds. It looks like it's somewhat shy, but I'll just call it 4 seconds. So time-wise, it looks like the object starts here. So this is the start. So it's at 0 second mark, it's at 16 meters, at positive 16 meter position. And at the 12 meter mark, that's actually about 1 second. And then I'm actually going to just say this is, that 8 meter mark occurs at the 2 second mark. No, I can't really say that. There's a little bit, or so it looks like at the 2.5 second mark. At 2.5 second mark. Just trying to get a scale here. It looks like the so at the 2 second mark. So let me just try to fix the times. So it looks like this 1 second mark looks like it's something somewhat shy of this 12 meter mark. So I'm going to say here, this is about the 1 second mark right here. And then the 2 second mark almost looks like it might be at 10, 2 second mark, 3 second mark, and finally the 4 second mark is going to end here at the 4 second mark. So 3 seconds. So this is actually kind of hard for me to scale this. Okay. I'm just trying to get a pretty good number line in case. So what I'm saying is this 3 second mark doesn't occur. It occurs like almost halfway in between the 8 meter and 4 meter mark, right? So that 3 second mark is somewhere in between there, and finally it ends there. Okay. So it looks like it's traveling to the left, and it's going to travel a total distance. I'm going to use a vector for this next part. It looks like it's going to travel a total distance of so how far is that? Well, that vector is pointing to the left. It starts here, and it's going to end here. And it's going to end here at the 4 meter mark at 4 seconds. The end is the 4 seconds. The initial time is 0 seconds, right? So that length of that arrow, it looks like it's going to be a total length of 16 meters minus 4 meters, right? So the displacement of this arrow, and I'll use red to be consistent with the arrow, that arrow looks like it's a length of 16, total of like, what is that, 12? But the displacement is what we're worried about, which is going to be the positive 4 meter mark minus the positive 16 meter mark, which means that displacement vector is going to be a negative 12 meters, right? Which makes sense because that's to the left. And it's over a total time, delta t is going to be 4 seconds minus 0 seconds. So that's going to be delta t of 4 seconds, right? So that means the velocity is going to be negative 12 meters over 4 seconds, or negative 3 meters per second, okay? So the velocity is going to be delta x over delta t, and that is going to be negative, the displacement was negative 12 meters over 4 seconds. So 12 divided by 4, that is going to be negative 3 meters. So it went to the left 3 meters over the period of 1 second. Okay? So I'm just trying to get a sense. So this is an object that has positive positions the entire time, but has a negative velocity vector, right? So the interpretation of this vector here is going to be negative 3 meters over the period of 1 second. So that's why I was having a hard time. It's not, this unit from here to here is 4 meters. It was actually 1 meter shy of each one of these every time, until finally it landed right there. Interesting. Let's take that equation, and I'm going to do this. So we're going to take that y equals mx plus b equation, and we're going to convert that to our position versus time. So again, you're trying to predict the final y position, the final axis, the final y, so the y-axis is going to be position, so we're trying to predict the final position using the slope, which is going to be velocity. Delta t is going to be the x-axis, and that is going to be plus the initial position. Okay? So in this case, to predict the final position, well, the velocity is, it travels a distance to the left of 3 meters over the period of 1 second, times the any time in that period of time, plus the initial position. It started out at a positive 16 meter position. And so that's the equation that is predictive of this. If we check it, hopefully it'll be predictive. Let's find out where it is at the 2 second mark. So negative 3 meters times 2 seconds plus 16 meters is going to be, so that's negative 3 times 2, so that's negative 6 plus 16. So that'll be it. So that means at that point in time, at the 2 second mark, it should be at a position of 10 meters, which is about what we were thinking. At the 2 second mark, it was somewhere in between the 8 meters, a positive 8 meter position and positive 12 meter position. Interesting. Let's try another one. Go ahead and look at this graph, and I want you to interpret what is happening with this graph, okay? And I want you to try to fill out this number line, okay, and see how you do. Also create an equation. So now that you've had a chance to work on this, sorry about that, I had to break off and repost the little number line for you guys. So you've had a chance to work on this, and hopefully you've written an equation and you've tried to use this axis to kind of mark up your document. So this is an extension of our first graph that we were using. Again, this is 5 meters. I'm just going to start off by actually looking and interpreting the graph itself without looking at the red data points. It's 5 meters, 4 meters, 3 meter, 2 meter, 1 meter, 0, -1, -2, -3, -4. Okay? And again, this is at the 0.25 second mark, 0.5 second mark, 0.75 second mark, and then finally the 1 second mark. Okay, so it looks like the object starts off here, and I'm going to let me take a moment and actually transfer these the position axis to this x-axis. So this is going to be the positive x direction. This will be the negative x direction. This will be positive 1 meter, positive 2 meters, positive 3 meters, positive 4 meters, and that's all the way that direction. -1 meter, -2 meters, -3 meters, and -4 meters. Okay, so it looks like the object starts off at time 0, right here. This is time 0. It looks like it starts off at time 0 at the -3 meter mark. So this is the start. And then it looks like it ends at the positive 1 meter mark at 0 seconds, right? So that means it's traveling a total distance of -3, -2, -1, 0, and +1. Travels a total distance of 1, 2, 3, 4, +4 meters over that period of 1 second. Okay, so I'm going to actually put in an arrow too. You know what? This is being difficult. Do it this way. It looks like it travels a total distance, or a total displacement, I should say. Apologize. It should be a total displacement. So that vector starts here, so it's 1, 2, 3, 4. So that'll be a total displacement of +4 meters over the period of that 1 full second. So what I'm guessing is that this displacement vector is going to be +4 meters. Okay, so again, I'm going to do the formal equation, x final minus x initial. Okay, and so the displacement ends at the +1 meter mark. It began at the -3 meter mark. So it's minus a -3 meters. So that means the displacement is going to be 1 minus a -3. So it's going to be a +4 meters. Okay. Well, we know velocity is equal to displacement over time, and the total time in this case is going to be 1 second, and it had a total displacement of positive 4 meters. So that means it's positive 4 meters over the period of 1 second. All right, I think we've got this pretty much handled. So it was traveling to the right at a constant velocity. It started at the negative 3 meter mark. It ended at the positive 1 meter mark. Well, let's make an equation, a predictive equation out of this. Again, I'm going to do y is equal to mx plus b. But in this case, we're predicting final position. The initial, this is going to be velocity, delta t, plus the initial position, which is going to be x initial. So we're predicting the final position. It was traveling at a positive 4 meters over the period of 1 second, delta t, plus the initial position. It started out at not a positive position, but actually a negative position. Okay? And so this is the predictive equation. Pretty cool. Okay, let's move on. So this next slide, we're going to be looking at, really the point of this next slide is actually using a graph to now talk about what is the difference between average speed and average velocity. Okay, that has the point that is related to the displacement, but also the distance traveled. So let's create some equations to start off with. Again, we're going to create predictive equations, mx plus b, but really we're predicting final position, so I'm assuming, yeah, this is going to be a horizontal position. So it'll be velocity delta t plus the initial positions. Okay, well, as far as lines, we're going to have a first line that goes from this is line number 1, this is going to line number 2, and this is line number 3. So this is going to be about line number 1, line number 2, and this is line number 3. Well, here we go. It starts off at the 0 second mark. It starts off at a positive 10 position of positive 10 meters. Okay, and then it ends at a negative 20 meters. Okay, so let's try to figure out its displacement from the 0 second mark to what says right here is a 30 second mark right here. This is the 30 second mark. So it starts off here at 10, it ends at negative 20. So that's going to be, the end position is negative 20 minus positive 10. So that means its displacement here for this part, its displacement for the 30 second is going to be negative 20 minus negative 20 meters minus positive 10 meters. And so that means it's going to be negative 30 meters. Well, it traveled that distance of that displacement of negative 30 meters in the period of 30 seconds. Okay, so negative 30 meters over the period of negative 30 seconds, so it's negative 30 divided by 30, so that's going to be negative 1 meter over the period of 1 second, delta t, and that's the prediction equation for the final position. My t's look like x's here. So that's delta and t, and that's x final. Okay, so it looks like this object has a slope right here that is going to be negative 1 meter per second. Okay, let's try from negative 30 seconds, well, from 30 seconds to 40 seconds, all right? Well, its initial position at the 30-second mark is going to be negative 20 meters, right? It's negative 20 meters. It has no slope, so that's 0 meters over the period of 1 second, delta t, and that's the prediction equation for this guy right here. In the final part, it again, since it wasn't moving, it starts out at negative 20 meters and it ends at 0 meters. So the displacement here is going to be for the displacement for this part is going to be it starts off at an initial position of negative 20 meters, and then it ends at the 0 meter mark, right? So it means it looks like it's being displaced a positive 20 meters. And that's a positive 20 meters over the period of 40 seconds, 80 seconds minus 40 seconds, right? So that's going to be, what is that? A negative, a positive, this is 20 meters, so the velocity is going to be 20 meters over 40 seconds, which is 1/2. So this will be 1/2 meters per second, delta t, and that's the final curve fit. So that's 1/2 meters per second delta t. Rewrite that so it's legible. So this is going to be 1/2 meter per second. Okay. So, what is the total displacement over the whole time, starting from 0 seconds to 80 seconds? Well, you started out at positive 10 meters, right? And you ended at, I'll write a little bit smaller so I can actually fit this in. The displacement is going to be, you started out, well, you ended at the 0 meter mark, and you started out at the positive 10 meter mark. So the total displacement, even though it traveled all the way down here, so it traveled to the left, a total displacement of negative 30 meters, didn't move, and then traveled to the right another 20 meters. Even though it did all that, its displacement is only negative 10 meters to the left. So it actually just traveled to the left from beginning to the end. So it ended right here. So even though its displacement is only 10 meters, its distance traveled now, it traveled down, it traveled to the left 30 meters, like 30 meters, and then it traveled back to the right 20 more meters. So the total distance traveled now, and actually I should just use a sum. The sum of the distance traveled, not the displacement, but the distance traveled, is it traveled 30 meters. It traveled 30 meters to the left, and then 20 meters back to the right. Is going to be a total of 50 meters. I'm not putting a positive or negative because distance doesn't have that. It's whatever's on the odometer of your car, right? Okay, so average velocity now is going to be your displacement over time, which in our case is negative 10 meters over the period of 80 seconds, which is going to be negative 1/8, an eighth of a meter to the left over the period of 1 second. Your speed is going to be your total distance traveled over time, and I'm going to use an S for speed. V is velocity, it's a vector, which is 50 meters over the period of that 80 seconds. So this is going to be 5/8 of a meter per second. 5/8 of a meter per 1 second. Okay? So that was the difference between average velocity and average speed. And here's how you kind of do those. There's some of those sapling or homework problems where you have a graph and you have to determine velocity and displacement from that. Okay? And so that's how you do it. Just establish your displacement for whatever time period that they're asking for. Establish the distance traveled for whatever time period they're asking for. And then for velocity, you do displacement over time. And then speed, you do distance traveled over time. Okay? All right. So this next slide, I wanted to give this to you. Sorry about that. So I want to put this example on here where you have a person skating. Okay, you have essentially you have two students on rollerblades. Okay, and you have to determine their velocities. So, in this problem, you're actually given this graph, and they're basically saying here in this graph, you have the first person that was traveling. It looks like the first skater had a displacement of 6 meters over the period of, it looks like, actually, that is going to be 5 meters. It's not ending here quite like we thought. So at the 1 second mark, they're ending at a position at positive 7 meters. So they start out at positive 2 meters, they end at a positive 7 meters over the period of 1 second. So that's a displacement of positive 5 meters in the period of 1 second. So their slope of their line is positive 5 meters over the period of 1 second. Okay. This next person starts off at a positive 1 meter position and ends at a negative 1 meter position at the 1 second mark. All right. So their displacement is going to be negative 1 meters, and so their velocity is actually, their displacement is going to be negative 2 meters. They went to the left 2 meters over the period of that 1 second. So their velocity is going to be negative 2 meters per second. Okay. And so that's what this interpretation is. So that's kind of what they're talking about here. So they're talking about the first skater that was traveling to the right, and they traveled to the right a displacement of 5 meters, positive 5 meters over the period of 1 second. And the other skater, skater B, was traveling to the left a total displacement of negative 2 meters over the period of 1 second. And so I just wanted to put that. I just wanted to put that on there as an example that you could read through to just reference on what we've been doing. Okay. Let's talk a little bit about instantaneous velocity. Now, instantaneous velocity is going to be at any given point. What is the slope at any one of these given points here? So I'm going to just put some points right here. And let's continue this line on this way, right? An instantaneous velocity is a tangent line at these points. So right here, I'm going to draw a little tangent line. So that's this right here, this is going to be a positive slope. So at this moment, it's got a positive instantaneous velocity. And so this is for more like our calculus students. An instantaneous velocity is just the derivative of the position versus time, right? So you take the derivative of the so at this point right here, you take the derivative at this position at this point in time right here, and you get that slope. Well, the instantaneous velocity here is going to be less. It's going to be more leveled. It's not as steep, so the object is traveling really fast in the positive direction. and then it looks like it's going to be slowing down, so its velocity vector is going to be smaller but still pointed to the right. Here, and this is for college physics students, you could also look at the slope here, and the slope here looks like it's going to be like 0 meters over the period of 1 second. So it's going to have no velocity vector, dropped off to 0. The object came to a stop. At this point, it looks like it started to travel to the left, a very slow level, but then it came to a stop again. It looks like this tangent line is going to be a 0 instantaneous velocity again. And then finally, it starts traveling back to the right at a little bit more steep level than it was right here. So instantaneous velocities are slopes at a specific point, and that slope is a tangent line at that point. That's different from the displacement. That's different from the average velocity vector. The average velocity vector, if you started here, you ended here. Well, you started here, you ended over here. The average velocity vector for this entire trip is going to be right here. Okay. Wow. While the average velocity can be is a lot of times is not the same as the instantaneous velocity unless you're traveling at a constant velocity. Obviously, since your velocity is changing its steepness or its speed, but it's also changing its direction over the entire course of this weird position versus time graph, your average velocity and your instantaneous velocity aren't going to be the same. So I wanted to talk a little bit about the difference between instantaneous velocity and average velocity. Okay, and we'll get more into that when we do problems later on. Okay. Well, this is one of your lecture tutorial problems that you're going to have to do later on. And I just wanted to take a moment to show you how to do it. Okay. So what you're supposed to do is read the prompt and then translate this prompt into a graph. Okay. So here we go. Here's a prompt. It's got a slow constant speed to the left and then a fast constant speed to the right. So a slow constant speed to the left. So I'm going to draw some graphs of position versus time. So to put some reference to what I'm about to say. And we're using horizontal position, so left-right position versus time. Try to make these all the same. So a fast constant speed is going to be very steep versus a slow constant speed and a positive velocity. So this is a very fast positive velocity, and this is a slow positive velocity. 2 positives, 1 positive, right? A very steep velocity to the left is going to have a negative, couple negatives, versus a level, which is just a negative velocity. So this is fast, and these two are slow. This is to the left, and this is to the right. Okay? So we're supposed to kind of combine two things. So this is one object, two different types of motion. So it looks like it's going to be it's going to be traveling to the left, so its positions are going to be decreasing with time, a level amount. And then I'm going to say it's got a negative slope, just like I'm drawing here. So it's got a negative velocity, so that's slow. And then something happens, and I'm going to do it at the second mark. And this is arbitrary where I place it. You could slide this whole thing up and down. It could be up here or it could be down here, right? But I chose to put it right here. And then it's going to have a fast constant speed to the right. So it's going to have very steep positive slope. So this is a very positive slope. So the more steep it is, the faster it is, the more level it is, the slower it is. Positive slope is to the right, negative slope is to the left. And so you're supposed to do something like this, okay? And there you go. There's a good example of your first tutorial. All right. Good luck, everybody.